Hi dear students, welcome to the next sessions from magnetic effect of current. Last class we have learned about Ampere's law and its application, magnetic field at various point in a solid cylinder, magnetic field at various point in a hollow cylinder and a problem, and for each of them we have seen one graph also. So today also we are continuing the second part of Ampere's law, but we are going to derive some special cases, something related to solenoid, something related to toroid, etc. So we'll start. The first topic is called solenoid. What is called a solenoid? Solenoid, normally in your book binding and all, you will use the spiral binding, right? That spiral like or a spring like structure of a copper wire or any conducting material is called a solenoid. Okay, so solenoid is nothing but a curling structure of a wire. So what we are going to find out, magnetic field, we are going to find out magnetic field along the axis of a solenoid, along the axis of a solenoid. To apply this one, we are using something called Ampere's law. Okay, here the first few things we are pointing out using Ampere's law. We are using Ampere's law to this purpose. Okay, and we know this is a coil, and coil carrying a current of I ampere, and coil have n number of turns. There are one turn, second turn, third turn, fourth turn, right? There are n turns. The coil will have n turns. And magnetic field outside of the coil is equal to 0. So these are the few assumptions or few parameters we are taking care while we are going to find out magnetic field along the axis of a solenoid. So magnetic field along the axis of a solenoid using Ampere's law, and coil will carrying a current of I ampere, coil will have n number of turns, and magnetic field FIELD, magnetic field outside of the coil will be equal to 0. So we have to assume a coil is placed will be here. So let's assume I have a coil like this, and coil is placed here. Okay, now a coil is placed in a uniform magnetic field. A coil will be there, and the coil is carrying the current like this. Okay, so the coil is carrying the current, and the current is flowing through the coil like this. It is rolling out and coming out. So now what you have to see from this point of view, you have to assume a coil which is in curling position. So you are an observer, you are looking from here, and you are looking from here. What you can see means from the top side currents are coming like this. See, currents are coming like this. If currents are coming like this, to find out magnetic field, what we'll use? We'll use right hand thumb rule. So in the right hand thumb rule or right hand palm rule, so the currents are going down. If the currents are going down means my thumb is going down. Now you can see my fingers at this point, at the central axis, my fingers are going where? Inside. So your currents are coming from the top like this. The currents are rotating. If the currents are rotating, so at this point you can see your thumb is coming down, because your current is from the top, it is turning and coming down. So your thumb is coming down means your other 4 curling fingers in this side is going towards that side. So which means the magnetic field at the central axis is pointing in this direction. Okay, now to find out the magnetic field intensity using Ampere's law, what we require to have? We require to have an Amperian loop. Now this is a central axis. So by including the central axis, we need to have an Amperian loop. So let's consider an Amperian loop like this. Amperian loop is naming A, B, C, D, A. So my Amperian loop is ABCDA. Now what we are going to do, we are going to apply we are going to apply Ampere's law. So what is Ampere's law? Closed integral B dot dl will be equal to mu 0 times of current enclosed by the loop. Okay, so B dl. So over the surface what? A, B, C, D and back to A. So this is the closed loop. So this can be splitted into two components. So closed integral B dot dl. I am writing B dl cos theta. See here AB is the first part. So AB plus BC plus CD plus DA. 4 together will give rise to ABCDA closed path. Now I have one open path. So I am not putting it as a circle. I am putting half circle. So it's a half circle over the surface AB. So one piece I am taking AB. B dot dl. Magnetic field is in the direction. We are taking A to B. So AB is also in the same direction. So B dl cos of 0, because this is the length vector. Magnetic field is also in the same direction. Plus second one BC into again open integral. This is not closed integral, half circle means open integral. B into dl, length. Now length is like this, magnetic field is like this. What's the angle between them? Cos 90. So cos of 90 plus closed, again open integral, not closed integral, open integral. AB is over, BC is over. Next one is what? CD outside. So B dl. Okay, here what is the point means? Outside the coil there is no current, so there is no magnetic field outside the coil. So this factor itself I can just put it as cos theta. Here B itself it is 0. And the last one is open integral coming down dA. dA is involved because current is only this area. This area current is rolling. So it is dA. dA is length is like this one. So B into dl into cos of 90, because magnetic field is like this, length is like this. Both are perpendicular. This is totally equal to mu 0 times of current enclosed. Okay. These are all the factors we have. Now I am clearing the board, will be here. Hope you have noted these points already in your notebook. Okay. So let's continue. So B dl cos 0. So integral dl. Okay. So open integral of. So all these are going 0. So what all the factors will be here? 0. This is 0. And this is 0 and this is 0. So three things are going to 0, only one thing is open. So that is B dl will be equal to mu 0 times of current enclosed. Current the loop is I. So integral, open integral of dl will be equal to mu 0 times of I, and BL will be equal to mu 0 times of I. Next, this is for it is a coil, and coil consists of n number of turns. We can say this is for one turn. This is for one turn. So BL will be equal to mu 0 times of capital N into I. This is for n number of turns. A spiral binding, right? A coil will have large number of turns, n number of turns. N may be any number. So B is equal to mu 0 Ni whole divided by L. So this is the formula for to find out magnetic field intensity along the axis of a solenoid. This can be also written as mu 0 times of Ni. But you have to remember one important formula. N is equal to number of turns by length. This is important. This is important. Normally, if a number of turns is given, you do not substitute in this equation, you substitute in this equation. Capital N is called number of turns. Small n is not called a number of turns. Small n is not the number of turns, but capital N is called the number of turns. So when number of turns are given, you have to use this equation. Number of turns per meter length, or they are saying like 100 turns in 1 meter or 100 turns per meter. If some statements are there in the question, then you can use this formula, because N is equal to capital N by L. This is the magnetic field along the axis of an solenoid. Okay, solenoid may be any number of turns. Okay, n can be any value can be obtained, and this is along the axis of the solenoid. Okay, I hope you got understood what is mean by solenoid. Solenoid is something, it's very simple. It is like a spiral binding what you are used on your notebook, right? Fine. So mu 0 times of ni. Small letter n means capital letter N divided by length L. So remember that point. Okay. Fine. Perfect. Okay. So then we are going to see the next topic. The next topic is called toroid. Toroid. Toroid is also a solenoid, but the only difference is like a toroid, a spiral binding and formed in the form of a circle. That is called toroid. So we'll draw the toroid first. This is called a toroid. Okay, this is called a toroid. A toroid is nothing but a solenoid, but it is turned in the form of a circle. Now we are going to find out, again we are going to find out the magnetic field along the axis of a toroid. Along the axis of a toroid. We are going to find out magnetic field along the axis of a toroid. So where is the axis? Axis will be here. Axis will have a radius is equal to r. Now we are going to find out magnetic field along the axis of a toroid. Again we have to use what is we are using Ampere's law. So closed integral of b dl cos theta or b dot dl, both are same, mu 0 times of current enclosed. So closed integral, I told in a spherical structure the angle between b and dl is 0. In the last session itself I told. So b dl cos of 0 will be equal to mu 0 times of current. This is closed integral. So b into integral of dl is equal to mu 0 times of I. What is integral dl for a circle? Integral dl is equal to L is equal to 2 pi r. So 2 pi r times of mu 0 times of I. This is for one turn. So if there are n terms, b into 2 pi r will be equal to n times of mu 0 times of current for n number of turns. So the magnetic field B equal to n into mu 0 I divided by 2 pi times of r. This is for a toroid. If you compare these equations with a solenoid, this is same. Only difference is that here what is coming? Length L. We have written as L will be there. N by L we have written as small letter n. Instead of length L, what is coming in toroid called 2 pi r. Only coming is 2 pi r. Why? Because toroid is in the form of a circle. So magnetic field B is equal to mu 0 times of Ni. So the equation is look like same for both toroid and solenoid, but the only difference is like here n will be equal to capital N divided by 2 pi r. There n is equal to what? Capital N divided by length will come. But here capital N divided by 2 pi r will come. Capital N divided by 2 pi r will come in case of a toroid, but in case of a solenoid simply length will come. That is the only difference. So magnetic field along the axis of a toroid, magnetic field along the axis of a solenoid. Both are simple topics. Hope you understood. Next we are going to enter another important topic, and the topic is called force experienced by force experienced by a charged particle, force experienced by a charged particle in a magnetic field. Force experienced by a charged particle in a magnetic field. Okay, so what is this indicate? Let's assume, what is this indicate? Force experienced by a charged particle in a magnetic field. So already some magnetic fields are there. So let's consider I have a magnetic field here in the board like this. So what is this cross sign indicates? Magnetic fields are into the board. Magnetic fields are into the board. Okay, so I have a magnetic field. Next, what happened means I have a charged particles, positive charged particles called plus q. I am shooting to this region. I am just throwing. So let's connect it with the heading force experienced by. So this state that a force will experience by a charged particles in a magnetic field, which means when I throw a charged particle in an existing magnetic field, here magnetic fields will be here. What direction magnetic fields are? Magnetic fields are into the board. Okay, cross sign indicate into the board, dot indicate out of the board. So this is cross mark. Cross mark means into the board. If it is put like a dot like this one, then it is out of the board, in your case out of the paper. So here already a magnetic field exists, but that magnetic field is into the board. This is what we are saying. Next, what will happen means I am throwing a charged particle into the magnetic field. What will happen in these cases? This was the topic of discussion. What will happen in these cases? This will experiences what is called a force. Somebody is trying to pull or push. I can say it will experience a force. So in short, a magnetic field will create a force on the charged particle. Okay, let's see. So what we are going to here before going to do will be here. We are going to learn one more rule here, and that rule is called Fleming's left hand rule. So write on the heading on the side as a continuation of this one. You can write Fleming's left hand rule. Fleming's left hand rule. Okay, what is Fleming's left hand rule states that it's very important. Okay, you have to use your 3 fingers like this. Okay, so first one is your thumb, second one is your middle finger, and this one is your forefinger. Okay, so I am just representing this is your thumb, and this is your forefinger, and this is your middle finger. So 3 things will be there. This is representing your thumb, and this is representing your forefinger, and this is representing your middle finger. This is representing your thumb, forefinger, and middle finger. Okay, in short, you can look into my hand. Thumb is representing this one, and this is a middle finger, and this is a forefinger. What this law is states that you have to place your all first 3 fingers in perpendicular direction, means one with another makes 90 degree. If that is the case, then your forefinger representing the direction of magnetic field. So forefinger representing the direction of magnetic field, and your middle finger representing the direction of the motion of the positive charged particle, or it is called current. So this is the direction of motion of positive charged particle, or this is also called the direction of current. And your thumb representing something called FB. FB is called magnetic force. So this is called the Fleming's left hand rule. It's a very simple way. Okay, we don't want to learn it in a definition point of view. Okay, of course, if you remember the concept, you can derive as a definition. Fleming's left hand rule states that forefinger representing the direction of what? Magnetic field, and the middle finger representing the direction of what? Direction of positive charged particles or current. Then your thumb representing the direction of magnetic force, and FB is called magnetic force. FB is called magnetic force. Magnetic force is the force given by what? Magnetic field on a charged particles. We are going to apply this Fleming's left hand rule here. Hope it is very clear to you. We have 3 fingers will be there. Forefinger representing the direction of magnetic field, middle finger representing the direction of the current or the direction of the motion of the charged particle, and the thumb is representing the direction of magnetic force, FB. Next, let's see. The positive charged particle in this diagram is moving from left to right like this one. So what will happen? We have to use our finger. So I told the magnetic fields are into the board. So this is my forefinger going into the board. In your case, it is into the paper. And my middle finger is going from in this direction. Positive charged particle moving in the direction. So middle finger like this one. So what you can see, my thumb is going in upward direction. Thumb is going in upward direction means if a charged particle is as soon as entering into the magnetic field, it will experiences a force. What direction? It will experience an upward force. Somebody is trying to pull it. If somebody is trying to pull it means it will move with a force called FB like this one. Once the charged particle is moving in this direction, again I am going to apply Fleming's left hand rule. Thumb is inside, but now what direction the charged particles are moving? Charged particles are moving in this direction. So my charged particles are moving in this direction. You can see my middle finger, I changed the direction like this one. So thumb is going in this direction. Thumb is going to this left direction. So what will happen? The charged particle starts to move like this. Again we are applying the Fleming's left hand rule. Once we are applying the Fleming's left hand rule, we know magnetic fields are into the board and this middle finger representing the direction of charged particle and force is coming down. Force is coming down like this. So what will happen? The charged particle is pushed like this. Again I am applying the Fleming's left hand rule and my middle finger is going in the direction of arrow mark and my forefinger is into the board and you can see a force coming towards me. So what will happen? This will go like this. So this is what type of motion in physics? This is called circular motion in physics. This is circular motion, right? It is starting from one position and it is moving in particular direction and it is keep on moving. And this motion is called circular motion. And here the point is like when a charged particle enter into perpendicular magnetic field, it will experiences a magnetic force. So let's list down the points. The first point is like the first point. When a charged particle entering into what magnetic field? Perpendicular or parallel? Perpendicular. Entering into perpendicular magnetic field. Perpendicular magnetic field. It will experiences magnetic force. Correct? It will experiences magnetic force. What is that force value called? FB. This is the first point. When a charged particle entering into a perpendicular magnetic field, it will experiences a magnetic force called FB. And second point, the charged particle undergoes circular motion with, this point is I am going to write, it's important, with constant speed. This point is important, with constant speed, which means its speed is not changing. This is moving with a uniform speed, constant speed, or this is also in physics is called what? Uniform speed. So both are same. Uniform speed. So this is moving with the constant speed or this is moving with the uniform speed, and the speed is not changing. Okay, so hope you understood. When a charged particle is coming in this direction and magnetic fields are into the board, both are perpendicular. One is coming in the direction and another one is into the board. So both are making 90 degree. Then this will undergo what type of motion? Circular motion. Circular motion in the sense, once the charged particle is entering into the perpendicular magnetic field, it will start to rotate. It will never come out. It will be get trapped in the magnetic field. So in order to escape it out, in order to take it out, this charge out of the magnetic field, what I have to do? I have to stop this magnetic field. Then only I can take the charge out, else the charge is getting trapped and the charge is undergoing in circular motions with constants or uniform speed. Okay, hope this is clear to you. Next. Next, what we are going to see, a subheading under this main heading only. Now we understand the concept. This will undergo this one. So once you are writing on your notebook, you have to use your, I can say, your fingers in order to represent the directions, various mudras, right? Magnetic field consists of lot of mudras. Right hand thumb rule, right hand palm rule, it's also called, and it's also called Fleming's left hand rule. So these are the rules. Okay, next one, mathematical expression for, write on the heading, the next subheading under this main heading, mathematical expression for FB. FB is a vector quantity. Mathematical expression for FB. FB is called magnetic force, I told, right? Magnetic force, FB, what are the things FB? FB is a vector quantity. FB depends on, what are the things? FB depends upon the charge Q and magnetic field B, and one more thing that is depends upon is called velocity. Velocity means speed of the charged particle. So the expression for FB will be equal to Q is a scalar quantity, V and B, velocity cross magnetic field. This equation is important. Mathematical expression for magnetic field FB. FB magnetic field is depends upon the charge. Charge is a scalar quantity. Velocity and magnetic field. These two are vector quantity. This is velocity. If you don't know, you can write, else you can skip it out. And this is called magnetic field. This is called the magnetic field. So magnetic field and velocity FB is equal to Q into V cross B is the expression for magnetic field intensity. So hope this is clear, and from this one we are going to find out the direction of the magnetic field, magnetic force, using which law? Fleming's left hand rule. Now I'm sorry. Now FB is a magnetic force. FB is equal to Q into V cross B. Because of this force, the charged particle is undergoing what type of motion? Circular motion. In a circular motion, in laws of motions you are learning about, in circular motion there are two forces are exist. If it is outside, then it is called centrifugal. If it is inside, it is called centripetal. So always somebody should be available to hold the charged particle towards the center. Okay, always one force should exist like this one. What is this force? This force is called centripetal force. I know the centripetal force will be equal to magnetic force. Because of the centripetal force, or it is also in this context, it is also called magnetic force. Because of this only the charged particle is undergoing uniform circular motion. What is the general expression for this one? mv square by r. R is the radius of the circular path. V is the velocity. What is this one? Q into V into B into sine of 90. What is sine theta? V cross B. Okay, we know V cross B. V cross B will be equal to VB sine theta. Theta is the angle between, additional information, theta is the angle between V and B. Theta is the angle between V and B. See here, this is the direction of velocity and magnetic fields are into the board. Both are making, so one is coming like this in this direction and magnetic fields are into the board. Both are making 90 degree. That's what we are writing as 90. V and V will get cancelled, sir. So we got mv divided by r. mv divided by r will be equal to qb. mv divided by r will be equal to qb. So I need to expand this equations. We need to derive some set of equations. For that I need this space. Okay. So what is the equations for r from this one? R will be equal to mv divided by qb. This is an important relation. R equal to mv divided by qb. This is an important relations. Okay, next one. Next one. What is called r equal to mv divided by qb? Okay. Next, we know from the first year itself, P is called momentum. P is called the momentum. Kinetic energy Ke is equal to P square by 2m. One equations will be there. So P is equal to 2m into E. Putting. Okay. So kinetic energy E is representing. E is equal to kinetic energy is equal to P square by 2m. P is equal to root of 2me. We can substitute this for mv. mv is equal to root of 2me whole divided by qb. This is also the another relation for radius equations. Okay, this is also the another relations to find out the radius equations. Next one, time period. Next one, time period. Time period means what is normally we call it as? We call it as velocity is equal to distance by time. Time is equal to distance by velocity. In case of a circle, distance is 2 pi r divided by distance by velocity by v. So 2 pi r divided by, what is v from this one? What is v from this equation? V is equal to qbr divided by m. See, v is equal to, from this one, v is equal to qbr divided by m. This is one equations. Next, r and r will get cancels. We got 2 pi m divided by qb. This is the expressions for time period. Okay, expressions for time period. This is not over. We still has to continue. Okay, fine. So time period equations, radius equation in terms of momentum, in terms of kinetic energy relations. This we are learning from first year. Okay. So hope you remember first year topic also, because equally important for Neet. Okay. So next one. The continuation of this one. Frequency is equal to 1 by time period. It's 1 by time period, which is equal to qb divided by 2 pi m. Next one, omega is equal to 2 pi f. So 2 pi into f is equal to qb divided by 2 pi m. 2 pi get cancelled. So omega is equal to qb divided by m. This is another relation and this is the another relation. So these all are the various relations we can derive it from this one. So the relations between energy and radius and r with mv by qb, and time period equations t is equal to 2 pi m divided by qb, and frequency is the reverse of this one, 1 by t equal to qb by tm, and omega is equal to qb divided by m. These are the various relations which are available under the force experienced by a charged particle in a magnetic field. So whenever a charged particle is entering to a magnetic field, it will experience some force, and that force is known as magnetic force. How to find the direction of magnetic force? Using Fleming's left hand rule. So in short, today's sessions we have learned about 3 topics: solenoid, toroid, force experienced by a charged particles in a magnetic field. Lot of equations are there. You have to remember this equation. This is mandatorily, directly formula wise somewhere we have to use this one while solving the numericals. Okay, hope you understood today's sessions of the 3 topics. So learn it in a perfect and conceptual way. Okay, thank you.